Quiz example. Bhutan e-learning program welcomes all the children to this lesson. I am Pavitra Bhatrai and I'll be taking a physics lesson for Key Stage 5, that is for class 11 and 12 students. Today I'm going to teach you all about simple harmonic motion. Now under simple harmonic motion, I'll try to focus more on simple harmonic oscillator. Let's learn about energy in simple harmonic motion. In order to understand the transition of energy in simple harmonic motion, we'll try to take an example of simple harmonic oscillator. So let's learn more. Is energy stored in a body executing simple harmonic motion? Does the energy transfer takes place between kinetic energy and potential energy? Is the answer yes or no? Let's try to learn with the help of this flow chart. Each and every object possesses energy, either while moving or at rest. In the simple harmonic motion, the object moves to and fro along the same path. Do you think an object possesses energy while traveling the same path again and again? So what do you say? Is the answer yes or no? Think over. Okay, hope you have an answer now. Okay, let's see then. Definitely the answer is yes. We'll try to learn more in the form of a flow chart. Energy is stored in a body while executing simple harmonic motion. Definitely the answer is yes, and it is the energy in simple harmonic motion. And the total energy in the system is stored in the form of potential energy and kinetic energy. In the process of simple harmonic motion, in the back and forth motion, there is interchange of kinetic energy to potential energy. The key thing you have to remember here is that according to the conservation of energy, energy remains constant, but it can only change from one form to another. Okay, in order to derive the energy equation in case of simple harmonic motion, it's very important that we first derive the spring constant equation. Okay, so in the later part, when I will derive the spring constant equation, I will define what is meant by spring constant. So let's have a look how we can find out the spring constant equation. We all know that acceleration of particle varies with time in simple harmonic motion. Using Newton's second law, we can find the force which must act on the particle to give that acceleration. So I hope you all remember what is Newton's second law. Do you remember? So Newton's second law is given by the equation force equals to mass times acceleration. Right? I hope you remember the acceleration equation which we have derived in our previous topic. Do you remember? Okay. So if you remember, we are going to use the same equation we have derived, the equation value in this equation. So let's have a look at it. Okay, so if you remember, the acceleration equation we have derived in our previous topic was acceleration equals to 2 pi f the whole square times x with a negative sign. Okay, so we have our first equation ready. Now, in case of simple harmonic oscillator, okay, when you apply force, especially in case of extension of spring. In this concept, let's try to apply Hooke's law. So now what is Hooke's law? Hooke's law states that extension is directly proportional to the force applied. So now, in order to know what is the amount of force applied in order to extend the spring, we will try to apply Hooke's law. So Hooke's law in mathematical form is simply given by force equals to negative k times x. So here you need to understand x, we understand its displacement, but what is k now here? So k is simply known as spring constant. Comparing equation 1 and 2, let's have a look at it. What is equation 1 and 2 we have generated? So comparing equation 1 and 2, we get the value of k. Remember, on both sides of the equation we have negative sign, so it will get cancelled off. So we have the spring constant value as m times 2 pi f the whole square. Okay, so please remember what is the value of spring constant? M times 2 pi f the whole square. Now let's try to learn what is the spring constant. Spring constant measures the stiffness of the spring. How much force is required to extend the spring? So in case of heavy duty vehicles like truck, we use a higher spring constant value, and in case of objects like pen and toy cars, we use a spring with lower spring constant. So I hope the concept is clear. Once again, let's look at, or let's read the definition. What is meant by spring constant? So please keep in mind that spring constant is resembled by symbol K, and it measures how stiff and strong the spring is, and it's measured in Newton per meter or dyne per centimeter. I hope the concept is clear. Please keep in mind even the application of spring constant. Now our spring constant equation is ready. We can very well derive the energy equation in case of simple harmonic motion. In order to derive the equation of energy in simple harmonic motion, let's look into the material or the model that we are going to use to derive the energy equation in simple harmonic motion. So here I have taken an example of simple harmonic oscillator. So what is simple harmonic oscillator? Let's have a look at the picture. Okay, so consider a block and spring system which forms a linear simple harmonic oscillator, that is linear, which can be also called as linear oscillator. So how to design this? Suppose you are working in lab, and if you want to design a simple linear oscillator, it's very simple. Take a spring, fix one end at the rigid point and the other end to the block. Place it. Remember, we are not going to use it in the vertical manner, but we are going to use it on the horizontal table. So it forms a simple linear oscillator. I'm sure you are going to use this model when you'll be doing practical classes in class 12 as well as in 11 grades. Okay, after having learned the design of a simple harmonic oscillator, let's see how we can calculate the energy in this model. The energy in linear oscillator transfers back and forth between kinetic energy and potential energy, while the sum of the two energy, that is mechanical energy, remains constant. As I have already stated, as per the law of conservation of energy, the total energy, that's mechanical energy, remains constant. But what varies, what changes in the process is when the body is executing simple harmonic motion, the transfer of energy takes place. So the transition here is in between potential energy and kinetic energy. Okay, now let's have a look at the mathematical calculation part of the energy in simple harmonic oscillator or in simple harmonic motion. So here we have two components. In order to calculate the total energy, we need to calculate the potential energy in a simple harmonic oscillator and as well as the kinetic energy. Let's look at it one by one. First one, the potential energy of a linear oscillator depends on how much the spring is stretched or compressed, that is on displacement. So potential energy is directly proportional to displacement, and is given by the mathematical statement as potential energy equals to half k times x squared. I hope you remember what is k. K is simply the spring constant. And what is x? X is the displacement. Don't you know the values for both? So try to substitute these values. We know the value of spring constant as well as displacement. So substituting these values in the potential energy equation, we get a better equation. Let's look at it. So after substituting the value of displacement and spring constant, our equation gets simplified in a better manner. You have two choices here. Either you can substitute the value of k, spring constant, or leave as it is. Okay, now let's try to look at kinetic energy, how to calculate the kinetic energy in case of simple harmonic oscillator. So in simple harmonic oscillator, how to calculate kinetic energy is simply given by a mathematical equation, that is kinetic energy equals to half mv square. Here m represents the mass of the block and v the velocity. So when you set an oscillator, okay, when you move one block, so what happens? What is the velocity with which the block is moving? That will be purely given by kinetic energy. Let's look into the mathematical part. So the kinetic energy of the system depends on how fast the block is moving, that is on the velocity. So remember, we have derived the velocity equation also. Substitute in the formula, m you can keep as it is. So substitute the value of v, remember it's v square, square it. So we get the equation of kinetic energy as well. So let's look at it. What is the final kinetic energy equation? So kinetic energy equation is given by half k a square sine square 2 pi f, which will mark it as equation number 2. Okay, after having derived the potential energy equation and kinetic energy equation, now we are ready to calculate the total energy. Once again, before we go to the calculation of total energy, remember what we do in order to calculate, find out the value of these two. We have taken an example of simple harmonic oscillator, and by applying a force, we have tried to set the oscillator in motion, and in the process we have calculated the kinetic energy as well as the potential energy. Now let's try to calculate the total energy. Okay, here the total energy or the total mechanical energy is given by sum of potential energy and kinetic energy. Equation 1 and 2 is ready, which gives us potential energy and kinetic energy. So let's substitute this equation and try to find out the total energy. Okay, hope you know how to substitute. Yes, okay, let's try to work out. Okay, substituting the equation of potential energy and kinetic energy in the total energy equation, we get a new equation where we find some common term. Okay, so taking out the common term, what we get is we get a standard equation. What is that standard equation? Hope you must have learned in 9 and 10 trigonometry class. 9 and 10 trigonometry class. That is sine square theta plus cos square theta equals to 1. So let's try to apply here and let's try to see what happens. So the whole sum here, try to look at the highlighted portion here. This here, cos square theta plus sine square theta, here 2 pi f. Okay, please keep in mind here, this can be reduced to 1. So what is our ultimate equation then? We have the equation as the total energy of a simple harmonic equation is given by the equation half times k times a square. I hope you remember what is k. K is spring constant. What is a? A is the amplitude square. So it simply means the total energy depends on the spring constant as well as the amplitude part here. I hope it's clear. Okay, so now we have completed the derivation and we know the total energy equation in a simple harmonic motion. So that is equals to half k a square. Remember, in some books they use U as a symbol of total energy, but it is the same. So now let's have a look at this graph. This is the total energy graph, and what does it signify? Okay, so you can see that along the x-axis displacement is being plotted, and along the y-axis energy is being plotted. So this is one part of the oscillation. So one oscillation graph we have indicated here. What can you say about this graph? Well, it is very clear from the graph that at the mean position, the energy is completely, what can you say? Look at the graph and the colors. The mean position, the energy is purely kinetic, and at the extreme position, the energy is purely potential energy. But the key line here is the energy remains constant. The total energy is constant. Here, there is only transition between, there's interchange between potential energy and kinetic energy. Okay, let's have a better interpretation of this graph. So, according to the law of conservation of energy, it states that energy can neither be created nor be destroyed. Therefore, total energy is in simple harmonic motion will always be constant. However, kinetic energy and potential energy are interchangeable. The figure represents graph of kinetic and potential energy versus instantaneous displacement. The second conclusion we can derive from this graph is at the mean position, as I said earlier, the energy is purely kinetic, and at the extreme position, the energy is purely potential energy. What is the third conclusion we can draw from this graph? So, the third conclusion we can draw is at other position, kinetic and potential energies are interconvertible, and their sum is equals to half times k times a square. And the last conclusion we can draw from the graph given is the graph is purely parabolic in nature. Okay, now towards the end, let's have a look at one of the simulations based on simple harmonic motion. So you can have a look at this picture. All of you can focus on the slide here. Okay, in this simulation, we can vary the components, and then we can see how the energy versus displacement graph varies. So we have different graphs here. We have the displacement time graph, we have the pie chart, and we have the energy graph as well. So we will try to look into one of the factors. Let's reduce the value of spring constant, and let's see what is the nature of the graph. Okay, let me reduce it to smaller value. Okay, now what do you see? Let's try to check, let's try to run, and let's see, check the nature of the graph when you reduce the value of spring constant. Okay, what can you see now? See, when we have reduced the value of spring constant, we can notice that even the level of the energy reduces. So it is very clear that the factors on which the energy depends here is one of the key component is spring constant. Likewise, we can check for other components as well. We can see the variation in energy through this simulation. Hope you're able to get how we are able to trace the path and run through this graphical representation. Okay, now towards the end, we have listed down few questions for you all based on the content of the lesson that we have learned today. Please try to work out at home. So hope you have learned from today's lesson. See you in my next lesson. Thank you.